The nth derivative of the product of functions. We apply Leibniz theorem for finding nth derivative of the product of functions. Statement. Let u and v are two functions of x possessing nth order derivatives. The uvn, that means nth derivative of uv, equal to unv plus nc1 un minus 1 v1 plus nc2 un minus 2 v2 plus and so on ncr un minus r vr plus and so on ncn uvn. This is the Leibniz theorem formula. Now proof. Differentiate uv with respect to x. Already we know formula uv dash equal to u dash v plus uv dash. So uv derivative is uv dash or uv1, one time differentiation of uv equal to u1v plus uv1. U derivative v as it is plus u as it is v derivative. Next, second derivative uv, second derivative of uv equal to u1, again u1 differentiation is u2 and v as it is plus u1 as it is v differentiation is v1 plus u differentiation u1 v1 as it is plus u as it is v1 differentiation is v2, that is equal to u2v plus 2c1 u1 v1 u1 v1 plus 2c2 uv2. Here 2c1, that means 2 factorial by 2 minus 1 factorial into 1 factorial, that is equal to 2 factorial means 2 into 1 by 1. So that value is 2. So normally we write 2 u1 v1. So 2c1 value is also 2. So that's why you can write 2c1 into u1 v1 plus 2c2 value is equal to 1. So NCN value is 1. So that's why here place of 1 we can write 2c2 into uv2. Next, NCR means n factorial by n minus r factorial into r factorial. This is the formula for NCR. Therefore, the theorem is true for n equal to 1 comma 2. Suppose the theorem is true when n equal to m. So just substitute uv power m, nth derivative, that is equal to uvm equal to umv plus mc1 um minus 1 v1 plus mc2 um minus 2 v2 plus and so on mcr minus 1 um minus r plus 1 into vr plus mcr um m minus r vr plus and so on mcm uvm. This is the mth derivative of uv. Now differentiate. We can prove Leibniz theorem by induction, mathematical induction method. Now differentiate both sides with respect to x. So uv m plus 1, already mth derivative. So again differentiate means u m plus 1, that is equal to here um, again differentiation um plus 1 v as it is. Next um as it is v differentiation is v1 plus mc1 as it is um minus 1 plus 1. So plus 1 minus 1 cancel, um v1 as it is plus mc1 um minus 1 as it is v1 differentiation is v2 plus mc2 as it is m minus 2 plus 1, so minus 1 v2 as it is plus mc2 um minus 2 as it is v2 differentiation is v3 plus on mcr minus 1 as it is um minus r plus 1 differentiation is um minus r plus 2 vr minus 1 as it is plus mcr minus 1 minus r plus 1 as it is vr minus 1 differentiation vr minus 1 plus 1 minus 1 cancel vr plus MCR as it is minus r differentiation m minus r plus 1 into VR as it is plus MCR as it is minus r as it is VR differentiation is VR plus 1. So single term UV formula applies. Can apply UV formula. Okay. Next plus on MCM U differentiation U1 VM as it is plus MCM U as it is VM differentiation is VM plus 1. Now that is equal to here UM plus 1 V plus in these two terms UM V1 is common. So here 1 here MC1 1 plus MC1 into UMV1 plus MC1 next term MC2 common MC1 plus MC2 here common element is UM minus 1 and V2 plus and so on plus MCM minus R plus 1 MCR UM minus R plus 1 into VR and minus r plus 1 VR into MCR minus 1. So in these two terms minus r plus 1 VR is common. This one is common. Remaining MCR minus 1 plus MCR into minus r plus 1 into VR plus and so on plus MCM UVM plus 1. This is said equation 1. But we know that NCR plus NCR plus 1 equal to N plus 1 into CR. And also MC naught or NC naught value equal to 1. So, using this in equation 1, UM plus 1 into V. UM plus 1 into V as it is plus here 1 we can write MC naught plus MC1 means NCR plus 1. So we can write M plus 1 into C1 M plus 1 C1 UM V1 plus MC1 plus MC2 equal to M plus 1 into CM plus 1 into UM minus 1 V2 and so on M plus 1 here in these two terms M plus 1 into M plus 1 CR into UM minus R plus 1 into VR plus and so on plus M plus 1 CM plus 1 UM plus 1 and VM plus 1. So thus the result is true for M plus 1 whenever it is true for M. Hence, by induction method, the result is true for all values of n. This is the proof of Leibniz theorem.